Well, welcome back, and today we're going to look at molecular geometry versus electron geometry. So this is taking the work that we've been doing with shape and VSEPR and just building on it a little bit. Okay, so with this we need to recall what our bonding pairs are and our non-bonding pairs, and this diagram here gives us a nice little review of that and the ways that we can represent it. Okay, so we will again be looking at our linear, trigonal planar, tetrahedral, trigonal pyramidal, and bent or V-shaped. Now these are all the ones that we need to know for standard level. Okay, and if we have a look at these, this is just reminding us that we have 2 bonds, 3 bonds, so 3 bonding pairs, 4 bonding pairs. Okay, and then when we get to tetrahedral, we have 3 bonding pairs but 4 electron pairs overall. And then in this one, we can also have, this is a bent or V-shaped, where we have the 2 electron pairs involved in the bond and 4 electron pairs overall because we have the 2 non-bonding pairs. And we will look at that in more detail. Okay, so just a little bit of review, remembering that our covalent bonds are electrostatic attraction between shared electrons and positive nuclei. Okay, this is only occurring between non-metals. So if we're going to be looking for, is it a covalent or ionic or metallic, we need to look at what the elements are, find them on the periodic table, and then make our decision. Okay, and then from there, we treat the bonding in the way that it should for the type that it is. Okay, we can use Lewis dot diagrams or Lewis symbols, which are these ones here, where we put the valence shell electrons around the symbol, and then the overall Lewis structure is this, but remember we can use dots to show those lines as well, and then our structural formula is where we replace those bonding electrons with lines. So bonding pairs participate in the covalent bond, okay, so they're the ones that we represent with a line, and then our non-bonding pairs of electrons are the ones where we're using dots. So these are our bonding pairs, okay, and then these dots here are our non-bonding pairs. Okay, it's really important to get this straight because we need to be able to identify these when we're talking about geometry, okay. So VSEPR is what we've been doing, okay, remembering Lewis structures only give us a 2D structure, so they don't let us know how the molecule is arranged in space or its molecular geometry, okay, and molecular geometry is set by our valence shell electron pair repulsion theory, which is stating that electrons being negatively charged will repel one another to be as far apart as possible, and remembering that that non-bonding pair to non-bonding pair repulsion is greater than non-bonding pair to bonding pair repulsion, which is greater than our bonding pair to bonding pair repulsion. And that sets the way that the molecule is distorted. We need to remember, okay, that our bond angles, we do need to remember. So we remember tetrahedral is 109.5. Our bent is less than 120, okay, but in this case we can say less than 109 for water, and again less than 107 for ammonia, and there's plenty of tables in your textbook that help you to do that. And remembering that not all trigonal planars will be 120, okay? Remembering that the nature of the atoms and the type of the bond changes those angles a little bit. So we don't want to be reporting the exact values. We want to use this less than notation. So our electron domain geometry, this is what's new for us today, okay? And we need to look at the molecular geometry, which is our shape, okay, where we're looking at the bonds and just really looking at those bonding pairs. So the molecular geometry here, the molecular geometry will be our trigonal pyramidal. Okay, so that's our molecular geometry. We've got 3 bonding pairs and 1 lone pair. When we talk about electron domain geometry, though, we're actually looking at the number of electron domains, and electron domains can be either lone pairs or a bonding region. Okay, so we're talking about areas where we would find electrons. Okay, and these are always around our central atom. So if we look at water over here, okay, we can see we have 2 bonding pairs and 2 non-bonding pairs, but this means overall we have, overall we have 4 electron domains. Okay, so that means that we have 4 electron domains. In boron here, the BF3, we have the 3 bonding pairs, no lone pairs. So only our bonding pairs count. So we would say this has 3 electron domains. Okay, so I want you to pause the video, have a look at these other 2, methane, ammonia, and carbon dioxide, and write down how many electron domains you think each one has, and then we'll go through them. Okay, hopefully you paused the video and had a look, and with methane you worked out that it has 4 electron domains because we've got the 4 bonding pairs and no lone pair. With ammonia, it also has 4 electron domains because we have the 3 bonding pairs to the hydrogen and then the lone pair on top of the nitrogen. And then with carbon dioxide, we've got these double bonds here. So double bonds count as 1 domain. Okay, so in this case, we would have 2 electron domains only. Okay? So we can talk about electron geometry rather than molecular geometry. So if we look at the number of bonds on this one here, where we have a linear arrangement, we refer to the molecular geometry as a linear arrangement with 180 degrees. But we can see that it has 2 electron domains. So it will also have a linear electron domain geometry. Okay, remembering that beryllium chloride can also take that form. That's one of our other exceptions. Our trigonal planar, we're only going to have 3 electron domains because there's no lone pairs, so we will also have trigonal planar in terms of our electron domain geometry. And then tetrahedral, where we have 4 electron domains, it'll be a tetrahedral electron domain geometry. Okay, so essentially what we're talking about here is if there's no lone pairs on the central atom, okay, then the electron domain geometry is going to be equal to the molecular geometry. They will be the same. Okay, so if it has 3 electron domains, it will be trigonal planar, and we will find that that will also be the case for its molecular geometry. So no lone pairs on the central atom, molecular geometry and electron domain geometry are the same. Okay, when we look at water though, things are a little bit different, okay? We have a V-shaped molecular geometry, which we know it's bent because of the presence of the 2 lone pairs, which distort it away from normal, okay? But it has 4 electron domains, okay? Which means we will refer to that as a tetrahedral for 4 electron domain geometry. Okay, so it will have a bent molecular geometry, but a tetrahedral electron domain geometry. Okay, so this is where our molecular geometry and our electron domain geometry change because of the presence of lone pairs. Okay, so no lone pairs, electron geometry is the same as molecular geometry. With lone pairs, we need to count up the number of domains and then apply that to our normal shape. So if we have 3 electron domains, okay, it'll be trigonal planar for its domain geometry, and then but be bent shaped if we've got something like SO2. Okay, this is going to have a trigonal planar electron domain geometry. Okay, So our electron domain geometry is different to our molecular geometry if there's lone pairs present. So this is just a little bit on the nature of science and looking at those bond angles, which, as I was saying before, and it's worth you reading. This is from your textbook, okay? And essentially it's telling us to remember that things will be less than, okay, what we say they will. So in this case with the ethene here, we would say that this is trigonal planar around this carbon and therefore would expect these bonding angles to be 120. But we're actually going to write them as less than 120 because we can have some variation dependent on the structure of the overall molecule. And back on this slide here on the previous page, we can see that the bond angles is given as less than 120, less than 109.5, and less than 109.5 for our bent there. Okay, that's it for electron domain geometry and molecular geometry. Next up, we'll talk about resonance structures.